Hi, I'm Bob Hunt. KYSOR Cadillac has been an industry leader for over 60 years. As professionals in engine temperature control, engine protection, and instrumentation systems, we supply a wide variety of products to the on-highway and off-road vehicle markets. Engine protection systems is one of our product lines. We manufacture the most widely specified engine protection system in the industry, known widely for its high quality and dependability. But like any electromechanical equipment, proper installation and service is essential for safe operation. This tape will focus on system operation, on-vehicle troubleshooting, and bench testing. KYSOR engine protection systems fall into two groups, alarm only and alarm and engine shutdown. Alarm only systems monitor engine coolant temperature, engine oil pressure, and/or engine coolant level, and, in the event of a problem, activate audio-visual alarms to alert the vehicle operator. It is then the operator's responsibility to shut the engine down. Alarm and shutdown systems monitor the same engine conditions, activate the same audio-visual alarms if a problem occurs, but after the warning is given, if engine conditions reach a critical level, the system automatically shuts the engine down. After the shutdown, the system also provides a limited restart period so that the vehicle may be safely removed from the highway. During our discussion, we'll be using alarm stats, which are temperature sensors, and pressure stats, which are oil pressure sensors. The set point for an alarm stat is stamped or engraved on one of the hex flats. This one is set at 220 degrees Fahrenheit. The set point for a pressure stat is represented by the last two numbers of the part number. This one will alarm at 5 pounds. Since the many makes and models of engines have different operating characteristics, alarm stat and pressure stat set points are chosen according to a particular engine's maximum allowable operating temperature and its minimum allowable hot idle oil pressure. Our first alarm-only system is Series 9034, which monitors engine coolant temperature and engine oil pressure. The two sensors have only one terminal apiece, and when the switches inside them open and close, they make or break a connection between the terminal and ground. The 9034 circuit begins at the key switch and runs through the system fuse to the light and bell, so they both have 12 volts. The ground sides of the light and bell are wired together and connected to the alarm stat so that 12 volts is also present at this point. The final system wire connects the alarm stat and pressure stat together, so there is 12 volts present at the pressure stat. The pressure stat is normally closed, and this one is set at 5 pounds. If engine oil pressure falls to 5 psi or below, the normally closed switch connects the terminal to ground. This grounds the light and bell, and a low oil pressure alarm is given. If engine oil pressure remains above 5 psi, the normally closed switch is forced open. There is no ground to the light and bell, and thus no low oil pressure alarm. The alarm stat has a normally open switch, and this one is set at 220 degrees. If engine temperature remains below 220 degrees, the alarm stat normally open switch remains open. There is no ground for light or bell, and thus no alarm. If engine temperature should reach 220 degrees, the alarm stat switch closes, connecting the terminal to ground. The light and bell now have ground, and a high temperature alarm is given. So far, we've only talked about a system that uses simple mechanical switches to connect and disconnect the ground to warning devices. Our next alarm-only system, 9039 coolant level alarm, will serve as an introduction to the solid-state electronics used in many KYSOR engine protection systems. This is a one-way system that monitors engine coolant level, and it does so using this sensor, a coolant level probe. The probe is installed in a radiator tank or in a separate surge tank. As long as the probe is covered with coolant, it has a slight but measurable ground through the coolant. On the diagram, we show the probe being grounded like this. The rest of the circuit begins at the key switch and goes through a 4-amp system fuse. The circuit splits at the output end of the fuse, and one wire supplies 12 volts to the CLA module at terminal number 1. The other wire supplies 12 volts to the bell and to the light. The ground sides of the bell and light come together here and are connected to CLA module number 3 terminal here. In order to give a low water alarm then, the light and bell must find ground through the module. Whether or not the module gives a ground to the light and bell depends on the voltage at terminal number 2. This is a very low voltage, but it can be measured with a digital voltmeter. As long as there is coolant covering the probe, the terminal 2 voltage will remain low, about 0.7 volts, as you see here, because the probe has a ground. If a coolant leak develops and the coolant drops away from the probe's ground goes away and the terminal 2 voltage will climb, as shown by this digital meter. At 2.5 volts, the module triggers the low water alarm by grounding the light and bell through post 3 to post 4, which is the module ground connection. Think of the module as having a switch between terminals 3 and 4 that does this for us. Our next alarm-only system is the Series 9030 three-way system. It monitors engine oil pressure using the same single-terminal pressure stat that we've seen, engine coolant temperature using the single-terminal alarm stat that we've seen before, and engine coolant level using the coolant level probe. The main difference in this system is in the module. It's larger and it has 4 terminals across the bottom and 1 at the top. Think of the module as having a simple switch inside it. The switch is able to connect terminal number 1 to terminal number 3. In this illustration, it is open. The switch will remain open as long as 2 conditions are met. First, that there is no ground on terminal number 5, and second, that there is a ground on terminal number 2. Also, the ground on terminal number 2 must result in terminal 2 voltage staying below 3.5. The module is wired into the circuit this way. The key switch 12 volts passes through a 10 amp system fuse and reaches the module at terminal number 1. The switch between terminals 1 and 3 is open right now, so no voltage can reach the light and bell and no alarm takes place. The normally closed pressure stat in this system is set at 6 pounds. If engine oil pressure should fall below 6 pounds, the pressure stat switch closes and connects its terminal to ground. This grounds the wire connected to terminal number 5 and grounds terminal number 5. The switch inside the module closes, voltage reaches the light and bell, and a low oil pressure alarm is given. A similar process takes place for a high temperature alarm. The alarm stat in this system is normally open and is set at 210 degrees. If engine temperature reaches 210 degrees, the normally open alarm stat switch closes and connects its terminal to ground. The ground reaches module terminal number 5 through the wire and the module switch closes. Voltage reaches the light and bell and a high temperature alarm is given. A low coolant alarm begins when coolant drops away from the coolant level probe. As coolant drops away, the ground at the probe and at module terminal 2 is lost. As the ground is lost, the voltage at terminal 2 rises. When terminal 2 voltage reaches 3.5, the module triggers the low water alarm, closing the internal switch and giving voltage to the light and bell. A final characteristic of the 9030 system concerns the switch inside the module. It is designed to act as a circuit breaker in the event of an overload and will trip out at about 1.5 amps. We can fool the switch into tripping out by purposely shorting post number 3 to the ground terminal with a test light. Notice that the test light went out and will not come back on. In order to reset the breaker, we must first turn the key switch off, remove the overload, turn the key switch on, and the module is reset. We're now going to talk about troubleshooting, and we'll talk about this in 7 areas, starting with the most important and working our way down. The first troubleshooting area, and by far the most important, is when we have either the wrong alarm stat or the wrong pressure stat installed for the engine. This results in either false alarms when nothing's wrong or no alarm when something does go wrong. Remember that the warning temperature of an alarm stat is on one of the hex flats, and the warning pressure of a pressure stat is the last two numbers of the part number. Second troubleshooting area, false low coolant alarms caused by a bad probe location. On the conventional top and bottom tank radiator, the coolant level probe should be located on the center line of the top tank and as close to the bottom of the top tank as possible. Locations that are off-center or too high usually result in false low coolant alarms when going around corners or applying the brakes. When the probe must be located in a separate surge tank, it should be located at the lowest point in the tank. However, stay away from ports where hoses are connected. Third troubleshooting area, pressure stat location. KYSOR publication EP6 instructs you to install the pressure stat in the oil pressure gauge line, preferably in the cab for protection against vibration and corrosion to the terminals. In other words, the pressure stat will give you the best service life if it's remote mounted on this KYSOR bracket or a similar device. Direct mounting of the pressure stat on the engine usually results in oil leaks, false oil pressure alarms, and a short service life. KYSOR strongly recommends against this. Fourth troubleshooting area. On the 90-30 three-way system, overloading the module is a common mistake. As we said, terminal number 3 has built-in overload protection and will turn off to protect the module from damage. Using warning lights that are larger than specified or using more than one warning light will overload the module. Finally, using audible alarms other than those manufactured by KYSOR may result in an overload. If you need to use a larger alarm, contact us directly and we can show you how to use a relay to achieve this. Fifth troubleshooting area. This covers what to do in the event you have a 2- or 3-way system that is giving a continuous false alarm. Since most systems have only one warning light, you must isolate the cause. Start the engine and then disconnect the wire from the alarm stat. If this cures the problem, the alarm stat was at fault. If not, disconnect the wire from the pressure stat. If this cures the problem, the pressure stat was at fault. But if not, go to the control module and jumper the coolant level probe terminal to ground. If this cures the problem, then there is something wrong in the coolant level probe circuit. Either a broken wire, an ungrounded radiator, or you are actually low on coolant. The sixth troubleshooting area concerns mounting the alarm stat. The alarm stat has a 3/8 inch pipe thread, and if you need to mount it in a 1/2 inch pipe hole, a warning tag shipped with every alarm stat tells you that a special bushing is required. This is important. If you use a standard reducing bushing like this one, the stat will not be submerged deeply enough to accurately sense the coolant temperature. Notice how the correct KYSOR bushing does not affect the installed depth. Seventh and last troubleshooting area. Bench testing the CLA module and the module used with the 90-30 system. To bench test the CLA module, you'll need one of these wiring adapters. Connect it like this. Then jump number 1 post to 12 volts positive, but don't turn your key switch on at this time. Jump number 4 post to 12 volts negative. Connect the test light alligator clip to post number 3 and the test light probe to post number 1. Jump the number 2 terminal to ground, which of course is post number 4. When we turn the power on, the module should go through a brief self-test indicated by the test light flashing. Okay. To simulate a low water situation, disconnect the jumper wire from post 2. There'll be a brief delay, what we call a slosh delay. The test light should come on. Reconnect the jumper wire to post 2, simulating that the water has come back, and after a brief delay, the test light should go out. Any module that does not act like this has a problem. Next, let's test the module used on the 90-30 alarm-only system. Begin by connecting positive battery voltage to post number 1, negative battery voltage to post number 4, the warning light or test light between post number 4 and module post number 3. The test light should be on at this time. At this point, connect terminal number 2 in the front to terminal number 4, which is ground, and the light should go out. In the rear of the module, connect terminal number 5 to terminal number 4, which is ground, and the light should come back on. Any module that does not act this way is defective. That wraps up alarm-only engine protection systems. Let's now take a look at alarm and shutdown systems. All KYSOR shutdown systems begin with a key switch which is connected to a fuel shutoff. The fuel shutoff may be either an electric solenoid or a KYSOR air-operated actuator. With the KYSOR actuator, when the key switch is turned on, voltage reaches the solenoid valve, causing it to close, exhausting air from the cylinder and allowing the piston to retract. The linkage turns on the fuel and the engine can be run. On other installations, we have a fuel solenoid. When the key is turned on, voltage operates the fuel solenoid, which turns the fuel on, and the engine can be run. This type of fuel solenoid can be used with KYSOR shutdown systems as long as it does not require more than 3 amps to operate it as part of a 12-volt system. This is another type of fuel solenoid. It is quite large and requires well over 3 amps to operate it. Because of that, we cannot wire it directly like we saw with the first two. We must use a relay between the fuel solenoid and the shutdown system. We'll begin by connecting the key switch run wire to this terminal on the relay, so that whenever the key switch is on, that terminal is hot. Secondly, we'll ground the other control terminal of the relay, and although you probably can't hear it, whenever the key is turned on, the relay clicks. Okay. Thirdly, we'll connect a 12-volt battery supply with a 10-gauge wire to the common terminal on the relay. Now notice that this is hot regardless of whether the key switch is on or off. We'll connect the 10-gauge feed wire for the large fuel solenoid to the normally open terminal on the relay. We'll ground the large fuel solenoid with another large 10-gauge wire. Now, whenever the key switch is turned on, the normally open terminal of the relay receives voltage, gives that voltage to the fuel solenoid, and causes it to operate. We'll cut that key switch to fuel shutoff wire in half and add a couple of sensors. The alarm stat, or temperature sensor, will be the first. The setting on this one is 220 degrees Fahrenheit. That means it will give a high temperature alarm at 214 degrees and shut the engine down at 220 degrees. Electrically, it looks like this, with voltage from the key switch reaching the alarm stat at the C, or common terminal. The normally closed switch is the one set at 220 degrees. So as long as engine temperature remains below that, the switch is closed and we have voltage at the NC terminal. A wire connects alarm stat NC with pressure stat C, so there is voltage there also. The pressure stat setting is 5 pounds, as shown by the last 2 numbers of the part number. This means that it will give a low oil pressure alarm at 9 pounds and shut the engine down at 5 pounds. As long as oil pressure remains above 5 pounds then, the normally open switch is held closed and we have voltage at the NO terminal. This wire connects the pressure stat NO terminal with the fuel shutoff. So voltage is present at the shutoff, the fuel is turned on, and the engine is running. This will be the case as long as engine coolant temperature and oil pressure are normal. A closer look at the alarm stat reveals that the normally open switch will stay open as long as engine temperature remains below 214 degrees, and thus there is no voltage at the NO terminal. Now let's imagine that the engine is overheating. As the coolant temperature reaches 214 degrees, the normally open switch closes and voltage reaches the NO terminal. The NO terminal is connected to the alarms, in this case a light and bell, so voltage reaches them and a high temperature alarm is given. If the engine temperature keeps rising, eventually the setting of the normally closed switch will be reached, 220 degrees, and it will open. Voltage goes to 0 at the alarm stat NC terminal and every point downstream, including the fuel shutoff. The fuel turns off and the engine is shut down. A low oil pressure alarm and shutdown is similar. Let's start with a normal engine and then let the oil pressure drop to 9 psi. At this pressure, the normally closed switch in the pressure stat will close and voltage reaches the NC terminal. The pressure stat NC terminal is connected to the light and bell, so voltage reaches them and a low oil pressure alarm is given. As engine oil pressure continues to fall, the 5-pound setting of the normally open switch is reached and it opens. Voltage drops to 0 at the NO terminal and at every point downstream, including the fuel shutoff. The engine is shut down. What we have seen so far represents a complete two-way alarm and shutdown system, except for one very important item, a means of overriding the shutdown. An override will be necessary every time the engine is to be started, because a stopped engine is the definition of a low oil pressure alarm and shutdown. In the system we've been looking at, the 9-pound alarm switch is closed, the 5-pound run switch is open, the alarms are on, and the fuel is turned off. The simplest override is of the manual variety, and when we add this manual push-button override to the other components, the result is a 9033 alarm and shutdown engine protection system. The override button is connected to the system fuse so that it has voltage when the key switch is turned on. To start the engine, we depress the button, which closes the switch, applying voltage to the override circuit and to the fuel shutoff. The fuel turns on and the engine can be started. After the oil pressure comes up, the button can be released because the pressure stat normally open switch is closed and we no longer need the override circuit. This system, as we mentioned earlier, is referred to as the 9033 manual override two-way alarm and shutdown system. The next system we will discuss is the 9032 automatic override two-way alarm and shutdown system. The only difference between this and the system we just looked at is the override. By removing the manual button and substituting this electronic override module, we convert to a 9032 system. Here's how it looks with the module in the circuit. As shown here, the module has an internal switch between terminal 1 and terminal 3. When the key switch is turned on, terminal 1 gets voltage. When the engine starter is engaged, terminal 2 receives voltage because it is wired into the starter circuit. As soon as voltage comes up on terminal 2, the module switch closes, giving voltage to terminal 3. Terminal 3 is connected to the override circuit, so voltage reaches the fuel shutoff, the fuel turns on, and the engine starts. As the engine begins to run, the operator naturally lets go of the starter switch. The starter disengages, and at the same time, voltage at module terminal 2 drops to 0. When voltage at terminal 2 drops to 0, a 30-second timer begins to run inside the module. The module will keep the switch closed for 30 seconds after the starter is released, for 30 seconds of engine run time. When the 30 seconds runs out, the module will open the switch and disconnect the voltage to the override circuit. But by that time, the oil pressure should be up to normal, the pressure stat normally open switch should be closed. Voltage for the fuel shutoff comes through the alarm stat and pressure stat, so the override isn't needed anyway. After the engine is running, the alarm and shutdown functions of 9032 are identical to 9033. The same alarm stat and pressure stat circuit is used, so the only real difference is in how the engine is started. Let's turn now to the third alarm and shutdown engine protection system, the Series 9031 three-way. 9031 has a feature not found on 9032 or 9033, low coolant level alarm and shutdown. To accomplish this, 9031 uses the same coolant level probe that we saw when we were looking at alarm-only engine protection systems. The system begins at module terminal number 4, where the key switch circuit is connected. When the key is on, terminal 4 has voltage, and so does the pressure stat C terminal, as shown here. The module has an internal switch that can connect terminal 4 to terminal 3. Since terminal 3 has the fuel shutoff wire, when the switch is closed, the fuel will be on and the engine can run. We will call this the run switch. When it comes to starting the engine, we can operate the run switch the same way we did with the 9032 system. Engaging the starter causes voltage to come up on terminal 2. Voltage on terminal 2 causes the run switch to close and turn on the fuel. As the engine begins to run, releasing the starter causes terminal 2 voltage to drop to 0. As with the 9032 system, this causes a 30-second timer to begin running. During that 30 seconds, the module will be looking to see if engine temperature, oil pressure, and coolant level are all normal. If one of them is not, then the run switch will open after 30 seconds and the engine will be shut down. Let's now discuss what it is that the module is looking for that tells it that the engine is okay. First of all, the module will assume that engine oil pressure and temperature are okay if voltage appears on terminal 1. Second, the module will assume that coolant level is okay if there is a ground at terminal number 6. The ground at terminal 6 must be sufficient to keep voltage below 3.5 as shown here. Let's take a closer look at terminals 1 and 6 then, since they are so important. We get voltage to terminal 1 by using an alarm stat and pressure stat circuit. The pressure stat has voltage at the C terminal from the key switch. When engine oil pressure comes up, the normally open switch closes and we have voltage at the NO terminal, which travels to the alarm stat C terminal, through the normally closed alarm stat switch to the NC terminal, and from there to the number 1 terminal on the module. The module now assumes that oil pressure and temperature are okay. For coolant level, module terminal 6 is looking for a ground. It finds that ground through the wire to the coolant level probe and into the engine coolant. In this case, the ground is good enough to keep terminal 6 voltage below 3.5, and the module interprets this as coolant level okay. A complete system looks like this with a normal engine. Since oil pressure and temperature are okay, the pressure stat and alarm stat switches are closed, and voltage goes through them to module terminal 1. Voltage at terminal 1 means good oil pressure and good temperature. Since coolant level is okay, module terminal 6 finds a ground through the probe into the coolant, and terminal 6 voltage stays below 3.5 volts. Less than 3.5 volts at terminal 6 means good coolant level. Since all engine conditions are okay, the module keeps the run switch closed, connecting terminal 4, key switch, and terminal 3, fuel shutoff. The engine runs normally. Let's examine system behavior in the event of an engine problem, starting with oil pressure. The system we've been looking at has a -10 pressure stat. That means it will alarm at 15 pounds and shut down at 10 pounds. If oil pressure falls, the pressure stat NC switch will close at 15 pounds, giving voltage to the light and bell and causing a low oil pressure alarm. This is no different than what we saw with 9033 and 9032. If oil pressure continues to fall, the pressure stat NO switch will open at 10 pounds. This removes voltage from module terminal 1. As voltage vanishes from terminal 1, the module instantly opens the run switch, disconnecting voltage from the fuel shutoff and causing a shutdown. The process is similar if the engine should overheat. The alarm stat we're using alarms at 214 degrees and shuts down at 220. As engine temperature reaches 214, the alarm stat NO switch closes, giving voltage to the light and bell and causing an overheat alarm. Again, this is identical to the 9033 and 9032 systems. If temperature continues to rise, the alarm stat NC switch will open at 220 degrees. This removes voltage from module terminal 1. As voltage vanishes from terminal 1, the module instantly opens the run switch, disconnecting voltage from the fuel shutoff and causing a shutdown. Low coolant alarm and shutdown is somewhat different. As coolant leaks from the system, the ground at the coolant level probe goes away and the voltage within the coolant level circuit begins to climb. When the voltage at module terminal 6 reaches 3.5, the low water warning switch closes, connecting terminal 4 to terminal 5. Terminal 5 is connected to the light and bell, so voltage reaches them and a low coolant alarm is given. This situation will continue for about 30 seconds. If voltage remains above 3.5 for 30 seconds, the module will open the run switch and shut the engine down. Here is the last of the alarm and shutdown engine protection systems. It may be referred to as either 9038, 9041, or 9042. Don't let this confuse you. It's just that we have three systems, all based on the same module, this large steel box. 9038, 41, and 42 have several features not found on other KYSOR engine protection systems. Most of the unique features are because of the module design, so let's talk about the module a bit. First, this is the only KYSOR module that is designed to be mounted in the engine compartment. Second, the pressure stat is mounted inside the module, and it is necessary to connect an engine oil pressure supply to this port on the bottom. Third, these systems are available as either two-way temperature and oil pressure or three-way temperature, oil pressure, and low coolant. The two- and three-way modules are internally different but are almost alike externally. Finally, there is a system diagram on the face of the module. This, along with the part number, helps in determining whether you have a two-way or three-way system. A three-way system has this orange low coolant level wire shown on the diagram. On a two-way system, this will not be shown, and there is a blank spot on the connector at that point. Before we get into system operation, let's talk about the differences between 9038, 41, and 42. 9038 is in a class by itself. These are custom designed kits intended for specific vehicle models with specific engines. This brochure, KYSOR Publication EP4, lists the various kits. Each kit has a complete color-coded harness, the necessary items to plumb oil pressure to the module, and all the other hardware needed for the installation. 9038 may be two-way or three-way as desired. 9041 and 42, on the other hand, are more basic versions of the system. 9042 is the two-way system, and the kit contains the module, the alarm stat, and the warning device. 9041 is the three-way version, and its kit also contains the low coolant probe, and of course the three-way version of the module. Neither 9042 nor 9041 contains the harness or the installation hardware. These must be supplied by the installer. Let's begin our discussion of system function with a look at the two-way versions. The module we'll be using is part number 5047-00936-05. Consulting KYSOR Publication EP8 tells us that the pressure stat inside this module will alarm at 20 pounds oil pressure and shut down at 15 pounds. The system is wired like this, and the first point that should be noted is that the module has a constant 12-volt supply through the red wire to the module battery terminal. When the key switch is turned on, the module also receives voltage through the green wire at the terminal labeled key. When the engine is running, voltage at the key terminal goes into the module and through the pressure stat run switch. We are not going to show the pressure stat, but it's the same one used in all the other shutdown systems we've looked at. Voltage from the pressure stat appears at the module terminal labeled COM. Voltage from the module's COM terminal enters the black wire and reaches the alarm stat at the C terminal. Assuming normal engine temperature, the voltage goes through the alarm stat run switch, out the NC terminal, and to the fuel shutoff. So far then, this system is not that different from 9033 or 9032. The run voltage for the fuel shutoff has to go through an oil pressure switch inside the module and through a temperature switch. In the event of an oil pressure problem, the pressure stat warning switch connects to the blue wire on the module alarm terminal. Voltage reaches the warning devices and a low oil pressure alarm is given. As oil pressure continues to fall, the pressure stat run switch opens, removing voltage from the module COM terminal, the alarm stat, and the fuel shutoff. The engine is shut down. A high temperature problem is handled much the same. As engine temperature rises, the alarm stat warning switch closes and voltage is applied to the yellow wire or NO terminal of the module. Internally, this can connect with the blue wire or alarm terminal and a high temperature alarm is given. As engine temperature reaches the critical level, the alarm stat run switch opens, voltage is taken away from the fuel shutoff, and the engine shuts down. If you happen to have a three-way version of the system, then the orange wire and a coolant level probe will be present. As in all the systems we've looked at so far, the probe finds ground in the coolant, and a good enough ground is required to keep the module water terminal below 3.5 volts. In the event of a coolant leak, the ground at the probe is lost and the voltage at the module water terminal begins to rise. When water terminal voltage reaches 3.5, a low coolant alarm switch inside the module will close and key switch voltage is applied to the alarm terminal, the blue wire, and to the warning devices. A low coolant alarm is given. This condition is allowed to continue for 30 seconds. At the end of that time, the module opens an internal switch that disconnects voltage from the COM terminal. Voltage vanishes from COM, the black wire, the alarm stat, and the fuel shutoff. The engine is shut down for coolant loss. The features we have discussed so far are not unusual, and you would expect to find them on any KYSOR alarm and shutdown system. There are two features of 9038, 41, and 42, however, that are radically different from the other KYSOR systems. These concern the function of the alarms and the automatic override. The difference in the alarms becomes apparent when the key switch is turned on. There is only a slight beep at this point. If the engine is started right away, there will be another minor beep as oil pressure passes the warning setting of the pressure stat. This feature is called bellhop and is a big favorite with drivers. The alarms come on and stay on only when there is a serious engine problem, not when the key switch is first turned on. Concerning the override, these systems have something called instant on. This means that the module override switch closes as soon as the key switch is turned on, supplying voltage to the module override terminal, the white wire, past the alarm stat NC terminal, and to the fuel shutoff. If the engine is not started immediately, the override switch will stay closed for 30 seconds and then it will turn off. At this point, the override may be turned on again by engaging the starter. This brings voltage up on the start or brown wire terminal, which activates the override for another 30 seconds, turning the fuel on and permitting the engine to be started. Our final point about the 9038, 9041, 9042 series also concerns the override. For high temperature or low coolant shutdowns, the override operates as many times as the starter is engaged, giving 30 seconds of engine runtime for each engagement. But after a low oil pressure shutdown, engaging the starter gives only one 30-second override period. After that is gone, the engine shuts down and cannot be restarted. The intention of this feature is to prevent damage to the engine that might otherwise be avoided. After the oil pressure problem has been corrected, it will be necessary to reset the system so that the engine may be restarted. Resetting requires two people, one to hold the reset button down and the other to crank the engine. When the engine starts, let go of the reset button. The system is now ready to go. This concludes our discussion of alarm and shutdown systems as far as their layout and function goes. Let's now talk about troubleshooting. We'll talk about troubleshooting in 8 different areas, and the first 5 are repeats of what we saw in alarm-only systems. The first and most important factor is whether or not the correct alarm stat and pressure stat are installed for a given engine. On alarm stats, the shutdown temperature is stamped on one of the hex flats. On pressure stats, the shutdown pressure is represented by the last 2 numbers of the part number. The alarm temperatures and pressures, however, are shown in the various KYSOR publications. Compare the stats on your engine with the listings in the back of these KYSOR publications, EP7 or EP5 for 9033, 9032, and 9031. Use EP8 for the 9038, 9041, 9042 series of systems. The engine listings are according to module part number, since the pressure stat is inside the module. Remember, more false alarms and shutdowns are caused by incorrect alarm stat and pressure stat application than any other factor. You must have the correct item. The second troubleshooting area concerns coolant level probe location. With alarm-only systems, a bad probe location could cause false alarms. With alarm and shutdown systems, you can get false shutdowns as well. Third troubleshooting area, the need to locate the pressure stat at some place that is not on the engine. In alarm-only systems, a pressure stat mounted on the engine could cause oil leaks, false alarms, and short pressure stat service life. In alarm and shutdown systems, you also get false shutdowns. Troubleshooting area 4. In the very beginning of this section, we talked about 3 types of fuel shutoffs. 2 could be directly connected to the shutdown system, and 1 could not. That one has a current requirement that the KYSOR system cannot handle and must be installed using a relay. Always consult this page in publications EP7, EP5, or EP8. It will tell you how to determine if you need a relay and how to wire it if you do. If you do not use the relay when required, the problems will range from difficult starting to no start to destruction of the entire alarm and shutdown system. Area 5. Alarm and shutdown system alarm stats come with a warning tag concerning reducer bushings, just like alarm-only ones. Failure to follow these instructions may result in a system that does not work. Troubleshooting area 6. Engine cranks but will not start. This is many times traceable to problems in one of 3 module circuits: key switch, ground, and start. The key switch circuit is module terminal 1 on 9032 systems, module terminal 4 on 9031 systems, and the green wire key terminal on 9038, 41, 42. In all cases, the key switch circuit should act like this: 0 volts with the key off, 12 or so volts with the key on, and not less than 9 volts during 10 or 15 seconds of engine cranking. That last one is most important: 9 volts while cranking. If you don't have it, either the battery is low or there are poor connections. If voltage drops to 0 while cranking, this indicates that the circuit has been mistakenly connected to the key switch accessory terminal rather than to the run or ignition terminal. As we said, a no-start situation may also be due to a bad ground at the module. The best way of testing the module ground is to use it while testing the key switch terminal. That is, if voltage is good while using a battery ground post, but voltage goes bad when using the module ground, then we know we have a bad module ground. The ground for the 9032 automatic override module is straightforward. Terminal number 4 must have a wire going to a ground point. The 9031 module grounds through either of these brass eyelets on the mounting ears. Make sure the unit is mounted on a grounded surface and use big enough washers to cover the eyelet. If it must be mounted on an ungrounded surface, it will be necessary to place a ground wire under one or the other of the mounting bolts. For 9038, 41, and 42, the module grounds through metal mounting tabs. This module usually gets mounted on heavily painted metal surfaces, since it is normally found in the engine compartment. For that reason, paint is often a problem for the ground path, and you may find it necessary to scrape paint from both the mounting ears and the surface on which the module is located. Finally, under no start problems, we want to take a look at the cranking circuit input. This takes place at module terminal 2 for both 9032 and 9031 systems. For the 9038, 41, 42, this takes place at the brown wire or start terminal on the module. In all cases, it should be 0 volts with the key off, 0 volts with the key on, and not less than 9 volts while cranking the engine. Troubleshooting Area 7, false shutdowns. These are defined as any time the system shuts the engine down without first sounding the alarm. False shutdown is almost always due to a loose connection somewhere. It may be at one of the stats, the module ground, or the fuel shutoff, including the fuel shutoff ground. Physical inspection will usually find most of these problems, but occasionally you'll run into one that defies all attempts to find it. In that case, call KYSOR Technical Service. We'll be glad to help you with it, either over the phone or in person if necessary. Troubleshooting Area 8, module bench testing. This is similar to what we did in alarm-only systems, but this time we need an additional tool, a fuel solenoid to use as a load. Without a load, a module could test good when in fact it has a problem. Let's begin by testing the 9032 system automatic override. Step number 1, connect battery negative to post number 4 on the module and connect your battery positive source to post number 1. Connect the fuel solenoid load to module post number 3. Connect your test light or voltmeter to the fuel solenoid load and make sure both of them are grounded. Turn on the power, and at this point there should be no voltage at the fuel solenoid. Take a final jumper wire, connect it to post number 1, and briefly touch it to post number 2, simulating the start circuit input. The fuel solenoid should turn on, and the test light indicates that voltage has come up at that point. The voltage should remain for 20 to 40 seconds. At the end of that time, it should turn off. If the automatic override acts differently than described here, it has a problem. Next, let's bench test the 9031 alarm and shutdown module. Begin by connecting one of the module mounting ears to ground. Connect your key switch voltage source to terminal number 4. Connect the fuel solenoid test load to terminal number 3. Connect another jumper wire to terminal number 4, but don't connect the other end at this time. Connect a jumper wire between ground at the module ear and terminal number 6. And finally, connect a second test light to module terminal 5 and ground it at the mounting ear. Now when we turn the key on, notice we have a brief pulse of the test light at the fuel solenoid, but none of the lights are on permanently. First test, briefly touch the number 4 yellow jumper wire to post number 2. This simulates the start circuit input. The test light should come on, the fuel solenoid should come on for 20 to 40 seconds and should then turn off. Okay. Next step, take the yellow number 4 jumper wire and connect it to post number 1 and leave it there. The test light should turn on, the fuel solenoid should turn on and stay on. It should not turn off this time. Last test, remove the jumper wire to ground from post number 6. The test light, that's connected to post number 5 should turn on, simulating a low water alarm. 30 seconds approximately after this happens, this test light should go out and the fuel solenoid should turn off. A module that doesn't pass any of these steps has a problem and should be replaced. Finally, let's bench test a 9038, 9041, or 9042 module. We'll need an additional tool this time, a compressed air supply with an adjustable regulator and an accurate air pressure gauge. We'll have to be able to connect the air source to the oil port on the bottom of the module. Begin the test procedure by grounding the mounting tab on one end of the module. If there's any paint on there, make sure it's been scraped off. Then connect the fuel solenoid load wire to the override terminal, which is the 6th one down on the module. Take another jumper wire and connect that same override terminal to the common terminal, which is the 8th one down on the module, or the one at the very end. Okay. Take a battery positive wire, in other words, a wire that is hot all the time, and connect it to the battery terminal, which is number 4. Take a second test light and connect it to the alarm terminal of the module, which is the 3rd one down. Ground the other end of the test light at the mounting tab. Take another jumper wire to the water terminal on the module if this is a 3-way unit. This is terminal number 5. Take that jumper wire also to the mounting ear, so it will be grounded. All right, at this point we should have no voltage at the test load fuel solenoid, shown by the fact that the test light is off, and we should have no voltage at this test light, which is simulating the warning light on the shutdown system. Make a final connection, which is a key switch controlled voltage wire, to the key terminal on the module, which is number 2. Okay. Turn the key on, which will bring voltage up on that key terminal. We should see that this test light, the warning test light, stays off, and the fuel solenoid test light comes on, indicating that the module has turned the fuel on. This situation should remain for approximately 20 to 40 seconds. At the end of 20 to 40 seconds, the fuel solenoid test light should go out and the warning test light should come on. Okay, we passed that test. Next, take a final jumper wire, connect it to any convenient voltage source among all these jumper wires, and touch it to the first terminal, which is the start terminal of the module. Notice that the fuel solenoid turns back on, indicated by the test light, but we still have the warning test light on. This condition should remain for approximately 20 to 40 seconds, and then the fuel solenoid and its test light will turn off once again. And we passed that test. What we've done here is to fool the module into thinking that the engine has been shut down for low oil pressure and that the driver has used up his one allowed 30-second override period. So if we take that last jumper wire, connect it to a positive source, and touch it to the start terminal, no matter how many times we touch it, we can't get the fuel turned back on because the module won't let us have more than that single 30-second override period. So that part passes. Okay. Now we must reset the module for our next test. Go ahead and connect the jumper wire to positive. Reach around behind the module here where the reset button is. Push the reset button all the way in and touch the wire to the start terminal. The fuel solenoid again comes on, and when we release the reset button, the warning test light turns off. Okay. At this point, while the engine is still being simulated as running, go ahead and connect the compressed air supply and bring it up to at least 25 pounds. Okay. With everything connected as you see here, we should have no warning test light, and the fuel solenoid should remain on indefinitely. Now, vent the air pressure down to the point of the alarm setting on the pressure stat. This particular unit has a 20-pound pressure stat, so we should see the warning test light come on as the air pressure vents to that point. And it does. Continue to vent the air pressure until we reach the shutdown setting, which on this unit is 15 pounds, and note that the fuel solenoid once again turns off. For a second time, raise the air pressure back to above 25 pounds, and the condition should reverse. Next test, connect battery positive to the NO terminal on the module. This is the 7th one down next to the end. When you do this, the warning test light should come on every time you make the connection. Last test. Disconnect the wire to the water terminal, which is the 5th one down. As soon as you do this, the warning test light should come on, the fuel solenoid test light should remain on for 20 to 40 seconds and then go off. And in this case, the test passes. Any module that does not pass all of these steps has an internal problem and should be replaced. This concludes alarm and shutdown engine protection systems. The KYSOR systems are among the highest quality and most dependable items that you can purchase or specify for your equipment. But like all electrical mechanical systems, they can be dangerous to life, limb, or property if misinstalled or treated carelessly. The necessary information for safe operation is as near as the KYSOR publications or your telephone. If you need help, call the Technical Service Department at 616-779-7528. And by the way, keep them rolling.